Welcome students. Today we will study the chapter of magnetism. Magnetism is a property by virtue of which a substance can attract small iron things towards it. So, magnet is a substance possessing the property of magnetism, or it is a substance which attracts small iron things towards it. Every magnet has two poles, north and south. The distance between the two fictitious poles is called length of the magnet, and it is denoted by 2L. The straight line passing through both the poles of a magnet is called its axis. The straight line which passes through the center O of the magnet and perpendicular to the axis is called its equator. Magnetic poles have certain ability to attract the iron things towards it. That ability is called pole strength. It is denoted by small m and it is measured in ampere meter. The product of the pole strength and the magnetic length is called magnetic dipole moment, and it is denoted by capital M. Its unit is ampere meter square. Magnetic dipole moment is a vector quantity directed from south pole to north pole inside the magnet. Pole strength of every magnet of both the poles is equal. To distinguish the pole strength of north pole and south pole, it is indicated with positive and negative signs. Thus, the pole strength of north pole is plus m and the pole strength of south pole is minus m. Like electric intensity, there is a quantity called magnetic induction in the magnetic circuits. Magnetic induction is the vector quantity used to describe the magnetic field. It is expressed in Weber per meter square, and it is the force experienced in the magnetic field by a north pole of unit strength. In 11th standard, we have obtained two formulae for magnetic induction at a point in the magnetic field near a small magnetic dipole. These formulae were magnetic induction at axial point in a magnetic field, which is given as B is equal to mu naught upon 4 pi into 2m upon r cube, where mu naught is the permeability of the medium, which is nothing but allows for the magnetic forces to act. Capital M is the magnetic dipole moment, and r is the distance of the point under consideration from the center of the magnet O. Similarly, in 11th standard we got the formula for magnetic induction at an equatorial point. Thus, on the equatorial line, if a point is at distance r from the center of a magnet of dipole moment m, then the magnetic induction at that point is given by B is equal to mu naught upon 4 pi m upon r cube. This year, in the first article of the chapter, we are going to obtain the general formula for magnetic induction anywhere near a short magnetic dipole. Look at the figure. In the figure, point P is anywhere in the vicinity of a short magnetic dipole of two poles N and S having pole strength M and magnetic length 2L. So its magnetic dipole moment capital M is given by M is equal to 2ml. We are interested in finding out the magnetic induction at point P, which is neither on the axis of the magnet nor on its equator. It is in between the equator and the axis. So, if you join point P with the center of the magnet O, then line OP makes angle theta with the axis of the magnet. In such case, the magnetic induction at point P is given as mu naught upon 4 pi m upon r cube under root 3 cos square theta plus 1, where theta is the angle made by line OP with the axis of the magnet. This formula gives the magnitude of the induction at point P. The direction of the magnetic induction at point P with respect to the line OP is given as tan alpha is equal to half tan theta, or alpha is equal to tan inverse half tan theta. So alpha is the angle made by the resultant magnetic induction with the line joining the given point and the center of the magnet. Thus, the total angle made by the resultant at point P with respect to the axis of the magnet is theta plus alpha. From this general formula for magnetic induction at a point anywhere in the vicinity of a short magnetic dipole, we can obtain the two formulae which we studied in 11th standard. Now, these formulae can be obtained as special cases of the general formula. Imagine point P to be on the axis. Hence, angle theta made by line OP with the axis will be 0. Hence, cos theta will be cos 0 or 1. Hence, cos square theta is equal to 1. So 3 cos square theta is equal to 3, and 3 cos square theta plus 1 is equal to 4. Hence, we get the formula for B as mu naught upon 4 pi 2m upon r cube. This is the magnetic induction at an axial point. If the point is on the equator of the dipole, then the angle made by line OP with the axis of the magnet will be 90 degrees. Then, as theta is 90 degrees, cos theta will be 0, cos square theta will be 0, 3 cos square theta will be 0, and 3 cos square theta plus 1 will be 1. Hence, we get the formula as B is equal to mu naught upon 4 pi m upon r cube. This is the magnetic induction at an equatorial point. Now, let us find out the formula for magnetic potential near a short magnetic dipole. Basically, magnetic potential is the amount of work done to bring unit north pole from infinity to a point in a magnetic field against the direction of magnetic field. This is an imaginary or hypothetical definition because it is not possible to isolate north pole from the south pole. But for understanding purpose or to have an analogous definition to electric potential. Usually, the magnetic potential is defined like this. If point P is in the vicinity of a short magnetic dipole and line OP is making angle theta with the axis of the magnet, then the magnetic potential is given as V is equal to mu naught upon 4 pi m cos theta upon r square. This is the general formula for magnetic potential at a point anywhere near a short magnetic dipole. Now, there can be two special cases for the magnetic potential also. If point P is along the axis of the dipole, line OP will make angle 0 with the axis of the magnet. Hence, theta is equal to 0 and cos theta is equal to 1. And then we get the formula for magnetic potential at axial point as mu naught upon 4 pi m upon r square. If the point P is on the equator of the dipole, then line OP will make angle 90 degree with the axis. Then theta is equal to 90 degree and cos theta will be 0. Hence, magnetic potential at an equatorial point is always 0. The substances can be classified into three types: diamagnetic substances, paramagnetic substances, and ferromagnetic substances. Diamagnetic substances are the substances which are weakly repelled by the magnetic field when they are subjected to external magnetic field. For diamagnetic substances, the dipole moments at the nucleus of every atom due to motion of electrons cancel each other. Hence, the resultant magnetic moment of an atom is 0. When an external magnetic field is applied, the induced magnetic moments in the substance oppose the applied magnetic field. Therefore, the diamagnetic substances are repelled by the magnet. There are few important properties of diamagnetic substances. These are as follows. If a rod made up of diamagnetic substance is placed in a non-uniform magnetic field, it moves from stronger part of the field to the weaker part of the field. If a rod made up of diamagnetic substance is placed in a uniform magnetic field, it comes to rest with its length perpendicular to the direction of the magnetic field. When a diamagnetic gas is passed through two poles of the magnets, it spreads at right angles to the direction of the magnetic field. When a solution of diamagnetic substance is taken in a watch glass and is kept between two dissimilar poles of the magnets, there is a small depression observed at the middle of the liquid surface. When a diamagnetic liquid is taken in a U-shaped glass tube and one of its arms is held in between two dissimilar poles of magnets, liquid level in that arm is lowered. The magnetic permeability of diamagnetic substances is less than 1 and susceptibility is less than 0 or small but negative. Antimony, gold, bismuth, mercury, water, air, hydrogen are some of the examples of diamagnetic substances. The second type of substances are called paramagnetic substances. The substances which are weakly attracted by the external magnetic field are called paramagnetic substances. The origin of paramagnetism can be explained like this. For paramagnetic substances, the dipole moments due to motion of electrons in an atom do not cancel each other. Hence, each atom has a resultant magnetic moment. Each atom in a paramagnetic substance acts as a small magnetic dipole called atomic magnet. In the absence of magnetic field, the atomic magnets are randomly oriented. Hence, paramagnetic substances have zero resultant magnetic moment. When an external magnetic field is applied, the atomic magnets are oriented such that their moments are in the direction of the magnetic field. Hence, the paramagnetic substances are magnetized in the electric field. When the external field is removed, the alignment of the atomic magnets is disturbed and the paramagnetic substances lose their magnetism. Like diamagnetic substances, the paramagnetic substances also have certain characteristics. These are as follows. If a rod made up of paramagnetic substance is placed in a non-uniform magnetic field, it moves from weaker part of the field to the stronger part of the field. If a rod made up of paramagnetic substance is placed in a uniform magnetic field, it comes to rest with its length parallel to the direction of the magnetic field. When a solution of paramagnetic substance is kept in a watch glass and is kept between two dissimilar poles of magnets, there is a small elevation observed at the center of the surface. When a paramagnetic liquid is taken in a U-shaped glass tube and one of its arms is held in between two dissimilar poles of the magnets, liquid level in that arm is raised. When a paramagnetic gas is passed through two poles of the magnets, it spreads in the direction of the magnetic field. The magnetic permeability of paramagnetic substances is slightly greater than 1 and susceptibility is small but positive. Aluminium, manganese, platinum, chromium, oxygen, etc. show paramagnetic nature. The substances which are strongly attracted by magnetic field are called ferromagnetic substances. The origin of ferromagnetic property can be explained on the basis of domain theory. According to this theory, the ferromagnetic substances are made up of certain regions called domains. The directions of the magnetic dipole moments of all the atoms or atomic magnets in a domain are same. Thus, every domain has a resultant magnetic moment. But the directions of the dipole moments in a substance are random. So, the dipole moments of different domains cancel each other and the substance shows zero resultant magnetic moment. When a weak external field is applied to such a ferromagnetic substance, the domain whose resultant magnetic moment is in the direction of the external magnetic field starts growing in size at the cost of the others. So the domain boundaries change their positions. So the substance show some net magnetic moment in the direction of the external field. When this field is removed, the domain boundaries restore their original positions and the domains are once again arranged in such a way to give zero resultant dipole moment. Hence, the substance loses magnetism. When a strong external magnetic field is applied, the directions of the dipole moments of all the domains turn in a way such that all the domains are oriented in the direction of the external magnetic field. In this case, even if the external magnetic field is removed, the domains cannot restore their original positions and hence the substance gets permanently magnetized. The properties of ferromagnetic substances are like paramagnetic substances, but they are in larger amount. The magnetic permeability of these substances is much greater than 1 and the susceptibility is also large and positive. Iron, nickel, steel, cobalt and their alloys are ferromagnetic in nature. When a ferromagnetic substance is heated, the thermal random motion of the atoms in the domains is enhanced. So, the coupling between the atomic dipoles become weak. When the temperature is increased further, at a certain temperature, all the couplings between the atomic dipoles are broken and the domain structure collapses. The temperature at which the domain structure of a ferromagnetic substance is destroyed is called Curie temperature of that substance or Curie point. After this temperature, the ferromagnetic substance loses its magnetism and becomes a paramagnetic substance. For example, Curie temperature of iron is 770 degrees Celsius. Hence, below 770 degrees Celsius, iron shows ferromagnetic properties, but if its temperature is increased beyond 770 degrees Celsius, it shows paramagnetic properties. Similarly, Curie temperature of nickel is 360 degrees Celsius. Curie temperature of cobalt is 1150 degrees Celsius and so on.